Today's topic is on the forefront of many of our discussions with speaking with some of our customers who are redesigning or building from the ground up broadcast studios or large infrastructures and using RTS intercoms. The 211030 standard, AES 67, AES 70, Dante, what is this Omnia that we talk about, and the OCA Alliance. So what does all this really mean, and what do you need to know when discussing it with your customers? These are things that our incredibly qualified presenter, Mr. Ethan Wetzel, will cover for us today. So let me tell you a little bit about Ethan. Ethan has worked in the audio industry for over 30 years in various roles. He's been a system designer, technician, a user, a product manager, just an all-around technologist. Today, Ethan works in the platform engineering group here at Bosch, and he develops and supports core technologies used across the communication business lines and markets. Additionally, he serves as marketing and technical committees for numerous standard bodies and trade associations that develop and promote media network standards and associated technologies for the industry. This guy makes sense of all of this stuff for us, in other words. So without further ado, let me give it to our resident guru, Mr. Ethan Wetzel.
Wow, thank you, Greg. That was far too generous of an introduction, but I really appreciate it. From my side, to everybody who was kind enough to spend your afternoon with us, thank you for taking the time out of your day to hang out with us and talk a little bit about some technology. As Greg says, we're disappointed that we weren't able to see you all in person, but instead I'm joining you from my cave, as my wife puts it, the Museum of Obsolete Digital Recording Technology. So I'm surrounded here by things like mini discs and DAT players and ADATs. There's even a functioning Laserdisc player scrolled away somewhere in here. And that actually is sort of an interesting tie-in to some of the things that we're going to talk about today. When we look at the landscape of technology that we all work with on our projects, in our facilities, and with the day jobs that we all have, we touch a lot of different things, and we interoperate with a lot of different pieces of technology, lots of different products that support different pieces of that, and we need to find ways to tie it all together and try to actually make all of this stuff work so we can get our production actually up on the air. One of the things that's really, really industry leading about RTS is the breadth of technologies that we support to try to facilitate all of these different types of productions. So everything from AES standards to things like SIP and VoIP, G codecs, 711, 729, 722, and of course things like Dante, and going even beyond that to analog technologies like 4-wire and some of our own technologies such as Arvon. We've got one of the deepest benches in the industry for pieces of technology that are going to tie things together. One of the reasons that I think this is really so important is twofold. Number one, it's something that allows you as a customer and as a user to continue to expand, evolve, and grow your systems over time. You really get an amazing return on investment when you incorporate this equipment into your facility, because you can continue to use it and you can switch these things around as needed. The other thing that I think is really important is RTS is of course known for doing amazingly large-scale productions, systems, and technologies for our partners. But I think it's also important to note that we can scale up, but we can also scale down. So whether you're dealing with a small project, a medium project, or a large project, we have products and technologies that are going to be able to support you in whatever you're trying to do and however you're trying to incorporate the equipment into your plant. That said, this can become a really, really confusing landscape when we start looking at all of the different technologies that are out there for getting the ones and zeros across the wire so we can actually communicate with each other. And what we're going to do today is take a little bit of a deeper dive and try to unpack some of these technologies, try to break down some of the fundamental components that go into these, talk about why certain things are relevant, how they relate to each other, what some of these acronyms actually mean, and most importantly, when we hopefully get to the next trade show and are going around looking at different pieces of technology and different products and are seeing these blizzards of standards and protocols and acronyms being thrown at you, what are the things that you need to pay attention to, and what are the things that, frankly, you can just sort of skip right over and ignore? So with that, let's dive in, shall we? So beginning at the beginning, everything that we're talking about here today with the technology that's actually moving our content around in a media network is based on three fundamental building blocks. So we've got protocols, we've got standards, and we've got solutions. And those are all different pieces that relate to each other in different ways. And that's a very important concept to keep in the back of your mind when you're going out and actually looking at the cut sheets and seeing what different pieces of technology have been incorporated into a given product. Now, those building blocks are put in place, are developed, and are supported by a number of different players. So we've got the standards bodies, such as AES and SMPTE, that actually codify the standards that can get published and then are then handed over to manufacturers to do the implementations of. We've got trade associations that focus on promotion and education for people who are trying to use or implement these different standards and technologies. We, of course, have the manufacturers like us that need to put this into our products. We need to maintain it, we need to support it, and we need to deliver these features to ultimately the most important people that are part of the conversation, which is you, the actual users and designers who are working with this stuff day in and day out, actually making things happen. The challenge, of course, is that it gets very, very complex. And Bosch, and specifically RTS, have been long, very, very enthusiastic proponents of standards and standardizing technology. We are very, very invested in time and technology and resources to promote, develop, and push along standards because we think that not only is this good for us as a company, but it's very, very good for you as users. Standards allow you to connect different pieces of technology from different manufacturers in ways that you maybe couldn't before. They also expand and grow over time. So as standards evolve, that evolution can move right into products that are already there. And just to show how serious we are about standards, it's become a default standard in the industry that anytime anybody talks about standards, they have to include this XKCD cartoon. So I'm flying the flag and I'm trying to do the right thing. All right, so let's really break this down to the fundamental core of what we're talking about. When we are hooking up that CAT cable or that fiber optic cable between two pieces of equipment, what we're trying to do is really create what we refer to as a media network. Now, a media network is going to be that fundamental architecture that's going to enable all of my stuff to talk to other stuff and actually move the content around. In order to do that, we've got really four primary services that we need to be able to provide and support on that wire and in those pieces of equipment that are connected to each other. So first off, we've got to be able to deal with the program transport, which is going to take my various pieces of content, it's going to encode it, it's going to manage it, it's going to actually put that content into packets and move that around on the wire so I can get it from point A to point B, C, D, and E, so on and so on. The second thing that I need, though, is once I'm actually moving around that content on the network, I need to be able to do certain things to it. I need to be able to interact with my devices. I need to do things like see VU meters and toggle crosspoints and matrices. I need to be able to view status. I need to be able to interact with those device parameters that are going on inside of the system so I can actually control everything that's happening. So fundamentally, program transport and system control are two halves of the same coin. In order to make all of that work, though, I need to have two additional complementary services that work with both of those technologies. At the beginning, I need to have time services. So time is something that is used for synchronization, making sure that things are arriving, playing out, and actually performing in a synchronized manner and keeping everything actually tidy and synchronized across the network. In order to do that, we use a number of different technologies, and that's something that applies equally to both transport as well as control. And last but not least, we need to have something that's referred to as a directory service. So when we're plugging together all of these different pieces of equipment, we need to actually be able to see who's out there on the network. What are they capable of doing? What are they doing right now? What are the services and functions that they're actually capable of providing? So that's where the directory service comes in. So all of these things together create what we refer to as a media networking architecture. We need to move our content around. We need to be able to interact with our devices. We need to keep everything synchronized as we're doing this, and we need to actually be able to keep track of who's on the network, what they're capable of. So in order to do that, we've got a number of different ingredients that go into a media networking architecture. These are based on those three building blocks that I talked about at the beginning. So at the very base, we have what we refer to as a protocol. And a protocol is a specific set of communication rules. These are things that are designed to do a specific task or job within a technical architecture. Some examples of this can include things like IEEE 1588, which is a time service, IEEE 802.11n, which I think we all know from Wi-Fi, TLS or transport layer security, HTTP. These are all examples of protocols, and these are created by specific bodies, standards bodies, for use inside of technologies. Now, a standard kind of builds upon protocols. A standard is an agreed upon way of doing things. And some examples of this can include things like AES 67-2015 or ST2110. What the important difference here is that a standard could actually be built up of one or more protocols. It's a way that I'm going to put things together or use certain things to achieve a specific task. So a standard can include a number of different pieces of protocols within it. And last but not least, we have what we refer to as a solution. Now, a solution is going to be an implementation of some of these pieces of technology. To paint a very broad brush, one could even look at something like a RTS key panel as a solution. It's an implementation that actually supports all of these different pieces of technology inside of it. But to sort of abstract that back a little bit to the world of media networking, you can also look at a piece of technology like Dante or Ravenna or QLAN or Bosch's own Omnia media networking architecture as solutions. Those are going to include a combination of protocols and standards. Some of those protocols are going to be standardized. Some of those are going to be proprietary. It really is all about the implementation of how these things have been put together, a bit like a recipe for baking bread or baking a cake. A good example of this, if we dig into what AES 67 specifically looks like, this is a high-level breakdown of some of the bits and pieces that actually go into AES 67. And as you can see here, this is a collection of a number of different protocols that actually make up the standard that is AES 67. So if there's one thing to take away from all this, remember that standards can include multiple protocols. Not all protocols are standards, and solutions can contain standard and non-standard protocols. It gets better from here, I promise. So let's talk a little bit about how some of these things actually relate to each other. When we are going to start implementing some of these protocols and standards inside of a solution, what we're really doing is building up a hierarchical structure where we're putting those building blocks together in specific ways to complement the overall feature set and the overall solution that we're trying to provide. These different building blocks build on each other and can nest within each other. And what we're really trying to do is create a complete picture to try to solve a problem. Again, going back to the recipe example, if we are going to try to bake a cake, I'm going to need my milk and my eggs and my flour and my sugar and my vanilla and. Those are those discrete building blocks that you're combining in specific ways to try to achieve an end result. And that's really what we're doing when we're building up a solution. Where this becomes really important, though, particularly as you go out and you begin to look at the world of standards and all of these different pieces of technology, is understanding how they relate to each other. So different layers, different levels of interoperability can be found depending on sort of what different pieces of technology have been included with each other. So, for example, if we look at something like a Dante device talking to another Dante device, I've got a very, very feature-rich solution there where I can be exchanging clock and audio and control information, and I can be using a common software GUI. I could do all of these different things because I'm using a common solution across both of them. Conversely, if I'm using a Dante solution with a device that just speaks AES-67, I can still exchange things like audio and clock, but I don't have some of those higher layer functionality. That's both a good and a bad thing. The downside is, of course, you get less feature-rich integration, but the good side is you get much, much more flexibility. So I can take that AES-67 solution, I could plug that into a lot more things than just a pure Dante solution. So you get flexibility versus feature richness. And as I say, generally, as you go higher up this stack and you get more and more and more common with these solutions, you're going to have higher levels of interoperability and you're going to have a more feature-rich solution. So when we start looking at how we compare these different pieces of technology, this is a really important relationship to understand. I get asked all the time, what's better, AES-67 or Dante? And it's sort of a misleading question because Dante can incorporate AES-67, so they don't compete with each other. AES-67 can be looked at as a subset of a Dante solution. So let's actually talk about some examples here, right? So if I'm trying to build up a media networking architecture, the first thing that I need to be able to do is, as we talked about earlier, move my content around the wire. So I could do that using a protocol like RTP. I can add some of those additional pieces, like a time solution, by adding IEEE 1588. So you can see that I'm adding these building blocks, these protocols, to try to achieve an end result. But I want to do more. So I want to be able to add some software tools to be able to manage my audio. I want to add things like discovery and directory. So I can add MDNS and DNSSD to get that directory and those discovery services going. I can then go even further. I can add additional tools for system management, device control, that type of thing. I can add things like RSTP for redundancy, TLS for security and encryption and inside of my solution. And if we begin to draw some boxes around how these different pieces relate to each other, we can begin to see this hierarchy. So, for example, the 1588 and RTP with some other things can be looked at as AES-67. If I add some of these additional tools like discovery and some of the software elements, now I can have Dante. And if I add some of these extra features, now we have what we within Bosch and RTS call Omnia. So you can see that these all interoperate with each other. And the takeaway here is because this is sort of a nested hierarchy, if I've got an Omnia device, that's capable of speaking to Dante devices and supporting all of those unique features that I have inside of their solution. But I can go all the way further down and I could talk to an AES-67 device and still be able to exchange audio with it. So as we move up the stack, we get more features. As we go further down the stack, we get more flexibility. So let's dig into a couple of these in a little bit more detail and talk about why they exist and what exactly they do. So fundamentally, AES-67 came around at a time that lots of audio over IP solutions were really coming onto the market. We had Livewire and WheatNet and Dante and Ravenna and a number of other things, all of which were kind of sort of doing the same thing. We're taking this audio content, we're putting it onto an IP network, and we're sharing it with all of the devices. But because they were all speaking different languages, we ran into this issue that even though they could all use the same networking infrastructure, they couldn't actually directly talk to each other. So we got into these really ugly situations where to get device A to talk to device B, you would have to do crazy things like protocol conversions. Dump that down to something like a MADI interface, or worst case scenario, an analog interface, just to be able to get the audio over the wire. So this mission of trying to put everything onto the network and be able to just exchange information really kind of broke down because we didn't have these devices speaking the same language, even though they were using the same networking equipment, fundamentally trying to do the same thing. So we looked at that as a industry and said, you know, this is kind of a problem. And as we began to really dig into the building blocks of each of these solutions, this is what we came across. All of them, again, are doing fundamentally the same thing and require the same kinds of building blocks to do what they need to do, to deal with things like clocking and synchronization and encoding and streaming and all of those different fundamental components that you need for a media network, but they were all doing it slightly differently. And because of those differences, nothing was able to speak to each other. So we began an initiative to go out and try to address this issue. And this is where AES-67 2015 wound up sort of culminating to develop a solution for this. So what this is intended to do is really address these core elements of a media network, things like clocking and synchronization, session description, connection management, transport, all of those different types of building blocks. We work to harmonize to actually build up something that could be used as an underlying standard to allow these pieces of equipment and these different solutions to be able to interoperate with each other. So by creating a baseline of common protocols within this standard, we were actually able to achieve interoperability between these different solutions that were already on the market. One important thing to remember about AES-67, though, is we drew very strict boundaries about what it was trying to do and what it was not trying to do. So our mission was to solve the content and clocking interoperability issue between the different pieces of technology. That's where it started and that's where it stopped. So we were not trying to completely recreate Dante, recreate QLAN or Ravenna. We were just trying to create an underlying layer that would allow these devices to talk to each other while still retaining all of the things that they did uniquely and they did well. So as a result, AES-67 does not include things like discovery or control or a dedicated software stack to be able to set up and manage your overall network. It was never intended to be a complete solution. It was intended to allow these complete solutions to be able to interoperate with each other on a base layer to move the audio back and forth. And that's what has happened. So as Dante and Ravenna and all the rest have incorporated AES-67, we're now able to get these different solutions to interoperate and talk to each other. So they complement the solutions that they're part of. AES-67 does not compete with them. And again, that's a very important concept to sort of bear in mind as you look at evaluating the different solutions that are out there on the market. So we've talked a bit about how exactly we can move the content around on the network, but what about this control thing? How are we going to interoperate with devices and the technology that we've actually got in the field once we put this content onto the wire? This is where AES-70 comes in. So some of you may have heard the term OCA. Now, OCA stands for Open Control Architecture. And way back when we and the broader industry started working on this going back in 2011, it needed a name. It didn't have a standard yet, so the name that we chose was Open Control Architecture. AES, once we began to work through that, we had a conversation with the AES, and they took the work, the protocol, and the specification that we had put together for OCA. We ran that through the AES standardization process with their vetting, their comments, and everything else that goes into that process for the AES, and OCA became standardized as AES 70. A good analogy to this is the technology known as MADI, which of course was standardized as AES 10. So AES 70 is the standardized version of OCA. And this was developed by a number of different members of the industry. We pulled together 12 different members from number of different areas within the industry to work on the specification, and then we took that to the AES to actually go through the standardization process. So AES 70 is fundamentally an object-oriented framework that allows the description and creation of control interfaces. What this does is create a standardized device object model that enumerates and depicts what exactly is going on inside of a device. Those are built up of what we refer to as control classes. So the different elements of objects or parameters that may exist within a device, such as a filter block or a matrix or a VU meter, those are examples of control classes that are described in AES 70 in a standardized way. And what winds up happening is because this is based on a standardized class tree, it self-generates, if you will, an API to be able to speak to, communicate with, and actually read out what's going on inside of a device. Alongside of all of that, it also includes, of course, an application protocol, so we could take that information and actually send it over the wire and communicate with the devices. Now, AES 70 is not a program transport. It is focused only on control, so this can live alongside Dante, Ravenna, analog audio, or no audio at all. It really doesn't care. It's got some features that allow additional operations with things like AES 67, or for things like connection management, but you don't have to tie this to any particular audio transport. It also doesn't mandate how exactly a programming model would be described. It doesn't mandate how a user interface would be described. It also doesn't define things like algorithmic details. So if I, as a DSP engineer, am going to create something like a high shelf filter, we are not going to mandate what exactly your math is going to be for describing the slope, for example. All we are doing is describing the object and giving people a way to actually interact with it. And last, of course, we do not mandate the use of specific device profiles. Because of the object orientation of AES 70, it becomes very flexible to be able to self-describe and self-enumerate a device. So if we dig into what exactly goes into AES 70 in a little bit more detail, there are managers, workers, agents, and network parameters. These are all different types of classes and objects that exist within a device to describe the functionality that goes on within that device itself. And this, again, is something that could be self-discoverable and could be actually advertised over the network. So it's very easy to see what exactly goes on inside of a device. Anybody on the call here who's ever had to deal with programming up a driver for an obscure piece of equipment to incorporate it into something like a Crestron or an AMX environment knows what it's like to read through that parser documentation and try to figure out the object indices or the hex values for the different objects that are going on within the device. AES 70 actually advertises all of that in a very human-readable way, and it's a standardized method of doing it. So you can actually see what's going on inside of a device just by discovering it. The device will come online, it will advertise itself, and it'll actually describe all of its objects and its parameters. So it's very, very easy to work with. Shifting gears, let's talk a little bit about ST2110. Ah, yes. And what is really going on here is a whole lot of work that's finally coming together to try to address a number of different challenges that go on within the broadcast environment. Now, as many of you know, working with different pieces of technology, using things like SDI and the sort of traditional technology that we've had inside of broadcast facilities for a number of years, it worked well, but there were some definite challenges with trying to work with these pieces of technology. Because we were dealing with things like single streams coming out of the device, it became a real challenge if you as a user needed to work with just one particular element of that content. For example, if we just want to pluck off the audio, do some edits to that, maybe some post-processing, and then get it back into the mainstream. This required a lot of additional equipment and a lot of additional challenges and complexity to try to build up a system that would actually do that. One of the biggest issues, though, was it had scalability issues, particularly as we're getting into new pieces of technology, and it was not something that could go directly over standardized networks. So from an infrastructure perspective, there were a lot of challenges that came along with some of this existing technology. As the industry looked at this, they identified those different things that needed to be addressed, and a number of different groups came together to try to sort of unpack all of those challenges and come up with some new ways that we could try to solve that problem. So from the beginning, I think it's really, really important to understand that ST2110 is not one single thing. It's a collection of a number of different standards and technologies. When some of this initial work was going on and trying to look at how this evolution to the IP-based broadcast environment was going to be, because there was a lot of work that needed to be done, and frankly, not a lot of time to get it done, it was very important to the groups that worked on this to try to not reinvent the wheel unless absolutely necessary. So there were a lot of initiatives to go out and look at technical solutions from a number of different places and try to choose the best in breed solutions or technologies that may already exist, either on the market or from a standards body that was out there. There was also a big focus on trying to choose standardized solutions to be able to include inside of this architecture, inside of what ST2110 would become. So as this technology survey was underway, one of the other things that everybody wanted to try to achieve was to create what's referred to as an essence-based streaming mechanism. So instead of having the single monolithic pipe that everything was carried on with a lot of challenges to mux and demux that content if you needed to work with it independently, essence-based streams really create unique streams for each of these types of data that exist on the wire, all of which are synchronized and all of which can be related to each other. So there's a stream for video, there's a stream for audio, there's a stream for metadata, there's a stream for clocking. All of these relate to each other, but they're also separate. So working with those uniquely and discretely becomes much, much, much easier with an essence-based architecture. So as this work went on to do this polling for the best-in-breed solutions, technologies from, of course, the AES, the IEEE, the IETF, all were pulled in to create this standardized suite. So it's also important to recognize that outside of ST2110, there are some additional technologies that can be used to support or augment what exactly is going on with this initiative. So an example of this is something like the Advanced Media Networking Association, or AMWA's NMOS technology. This is not currently a formal standard from SMPTE, but it is a piece of technology that's been provided by industry association to add some support for some of the things that are going on within ST2110. And NMOS itself is broken up into a number of different technologies. So things like ISO 4, ISO 5, ISO 6, all of those are discrete pieces of technology that fulfill specific roles within the environment itself. It's a longer list that goes on beyond this, but just to provide a high-level overview, additional information on this can be found on the AMWA website, of course. But to sort of switch back to ST2110 specifically, this is a bit of a view of the ingredient map of things that go into ST2110. And we can sort of see from the right moving to the left how we've had some of these initial pieces of technology that have been discovered, have branched off, and have incorporated themselves back into creating this umbrella or aggregate standard suite known as ST2110. The reason this picture, which is not complete, by the way, is important to understand is depending on the pieces of technology or the specific piece of equipment that you as a purchaser or a user are looking at, not all of these pieces of technology are going to be specifically relevant to it. So, for example, something like ST2022-6 or VSF TR03, those are technologies that are related to video. So if you're looking at something, for example, like a RTS key panel, we don't do video. So our implementation of an ST2110 solution would not include those pieces of technology. The reason I bring this up is when you have that conversation with a vendor or a technologist about what their support is for some of these things, just saying I support ST2110 isn't quite enough information to really understand if that's going to be appropriate for your solution. So dig a little bit deeper and inquire some of the specifics about how that support has actually been rolled out. To look at this in a little bit more detail, this is a higher level overview of the AIMS roadmap. AIMS is an industry trade association that supports the adoption and promotion of ST2110 and works with a lot of the contributing groups such as the AMWA, the Video Services Forum, the AES, SMPTE, a number of other groups. So it's a very diverse collection of people that are involved with this. This is an example of the AIMS roadmap for the broader IP transition in broadcast. And you could see here an overview of some of the different pieces of technology that go into this. So we could see here that things like AES-67 for audio over IP are part of the AIMS roadmap. And of course, this is the technology that is supported within RTS. Looking specifically at things like ST2110, though, we can also see that ST2110 itself breaks down into different components. So 2110-10 is the standard for timing and clocking definitions, whereas 2110-30 is their implementation of how AES-67 will fit within a broader ST2110 implementation. So let's talk about that relationship just a little bit. So we just said that ST2110-30 is essentially saying I'm going to use AES-67 for audio. And that is absolutely true. But one of the things that was done as the AES-67 standard was chosen is the ST2110-30 specification actually adds a couple of additional constraints and definitions for how AES-67 itself needs to be implemented within this environment. So those constraints actually add some additional features or implementation details that, again, you need to be aware of when you go out and try to look at how these things are going to interoperate with each other. So specifically, we're talking about an ST2110-30 implementation must support the ST2059-2 profile. It needs to support a zero value offset between the media clock and the RTP stream clock. And it's required to be able to force a device to operate in PTP slave only mode. Those are some additional constraints on top of the core AES-67 implementation that need to be implemented in order to call an AES-67 solution ST2110-30 compliant. And yes, that's a big mouthful of acronyms and numbers. But happily, this is all described in greater detail than what I've gone through here in a white paper that Ames has made available up on their website. So for folks that really want to get under the hood and understand some of these differences, I'd highly recommend taking a look at that white paper to see what exactly the details are. It does go a bit deeper into some of the specifics on this as well. But the core takeaway here is when you are looking at a device that says it supports AES-67 and you're planning on incorporating this into an ST2110 plant, please make sure that you're digging a little bit deeper again and asking, is that specifically ST2110-30 compliant? Okay, so as we've gone through all of this, this was a very high-level overview of the wonderful world of standards and acronyms and technologies and groups that go into all of this. There are a number of different players that go into defining, supporting, promoting, and actually implementing all of these different pieces of technology. One of the things that's very unique about Bosch is we actually are a key player in all of these different groups. And this includes groups not just relevant to the broadcast environment, but also looking beyond it into our pro sound markets, into other verticals, other industries such as security and technologies like OnVIF. We are involved with all of these. And not only do we actually devote time and engineering resources to implement all of them, but we are actively shaping and defining all of these standards. When these things are actually coming to market, additional standards are going to be enhanced, they're going to be expanded on, new ones are going to come along, and all of this stuff takes time to actually get from task group to document to silicon to product to testing to market. So standards are a wonderful thing, but it can take time for some of this to actually begin to roll out into the industry itself. So planning for standards is a absolutely wonderful thing, but try to always go into these decisions taking a very long view as to what your migration path is going to be going forward to get into sort of the broadcast environment of the future. I would be remiss if I wrap this up without talking a little bit about Omnia, which is the media networking architecture that comes from Bosch and specifically RTS as well. This builds on all of the concepts that we just talked about. So Omnia itself is a media networking architecture that is based on a number of different media transmission technologies. So this is fully compatible with things like Dante, with AES-67, and with other technologies, not just now, but things that will come in the future. It's been designed in a way that we can extend this very, very easily to make sure that there's always a migration and an evolution path going forward. To this, we also add system control with things like AES-70 and a number of additional technologies to try to create something that is very feature robust, but also highly scalable. So we could deal with mission critical environments of any size, large, small, tens of thousands of devices on a local, national, or even international basis. And then on top of this, we continue to add additional technologies, many of which are standards, such as using TLS for encryption and security in some of our markets and applications. Our approach here is to create an object-oriented architecture that can solve the solutions of today while also preparing you and your products and your facilities for the technologies and the standards that are going to come tomorrow as well. So it's a very future-looking architecture that supports different needs and is able to grow with you over time. So with that, I think we're at the Q&A point. So Greg, if we had anything pop up in chat, fire away. I'll also mention to the group here that we are joined as well by Sean Anderson, a guy who is much smarter than I am and will be able to field any specific questions about products or anything else that you might have that I may not be able to.
Awesome. Thanks, Ethan. We have 10 minutes to spare. Every time you do this, I get a little bit more out of it. And the good thing about you really have a good way of doing this, so much technical content in this very easy way to understand. And for our customers and people on the line here, we will have this, as I said, it's all recorded. So you can share this and look it over again yourself when you have some more time to pick up like I just did. A couple questions here. One for Ethan, I think. How does AVB differ from AES-67 and or AES-70?
Okay, always a good question. So I guess the first thing to do is decouple AES-67 and AES-70. So AES-67 is media transport. AES-70 is device control. They can work together, and they can actually complement each other, but they're doing two very, very different things. So we can sort of take that and set it aside, although AVB does have this 172211 AVDAC technology as well, which does some of the same things, but isn't quite the same. So I think the best way to answer this is make the comparison between AVB or Milan and AES-67. Fundamentally, at their core, they're very, very different pieces of technology in how they are actually dealing with the packetization of the actual digital audio to get that onto the wire. And that fundamental difference actually sort of rolls up into a lot of kind of higher level discussions and application differences between the two. Sometimes this gets oversimplified as saying AVB is layer 2 and AES-67 is layer 3, but I personally think that that's kind of an oversimplification that doesn't really address the specifics of what they're trying to do. Fundamentally, AVB, as I say, at the core is much different with how it actually deals with the packetization. But it goes a lot further in that it also incorporates a number of additional technologies that are there for network management. And this gets into the IEEE AVB suite that deals with things like stream reservation, traffic shaping, and a number of other things. The good news about that is it eliminates having to do things like work with QoS for actually making sure that streams can get through on your network. The, I guess, downside to that is in order to use and take advantage of those additional pieces that exist within the AVB suite, you need to have switches and technologies that actually support that. This gets into why you need specific AVB switches to work with AVB protocols, or AVB solutions, I should say. That's not a limitation for something like AES-67. This can work with off-the-shelf hardware. It's something that can actually be sent over subnets. You get that real routability solution. That's not to say that one is better than the other. They both do certain things well, kind of like how my DAT player and my ADAT player, one isn't necessarily better than the other. They're just designed for very different purposes. So when you are looking at the differences between the technologies, this again sort of gets into taking that long view about how you're going to evolve your production core and your environment to get to this network solution and really trying to choose the technology that is going to solve the problems that you have today, but also allow you to have that flexibility and scalability in the future.
Awesome. And I have two for Sean, two quickies here. Does RTS have ST2110-30 implemented already?
Yes, actually, we released the software to support the 2110-30 roughly April of this year. We've done some extensive interoperability testing with different companies. Grass Valley, Sony, several others. But yes, we did do a full official release just shortly before what would have been NAB due to the cancellation. Didn't have as much noise as we'd hoped to. But yeah, that's been released since April of this year.
Awesome. And then one more for you, Sean, before we take off. If I'm designing a system, an intercom system, what would determine whether I use the Arvon technology, RTS over network, versus the Omnia Dante? What would I need to think about before buying products with Arvon versus the Omnia?
Really, it boils down to the amount of delay in your network, or if you're going outside of your local LAN. Arvon is meant for long distance connections, typically through public internet. Doesn't really care about network delay whatsoever. Whereas Omnio is more leaning towards internal LANs where you have very, very good control over network latency. The other big difference, though, too, is audio quality. Omnio has full spectrum audio, 20 hertz to 20 kilohertz, whereas Arvon is typically, depending on the codec you use, around 4 kilohertz versus 7 kilohertz of frequency response. So really, the determining factors are mainly distance and audio quality, what would decide which one of those you'd want to go for.
Awesome.
Yeah, and I guess just to build on that, I think that's a really powerful example of why having this breadth of technical solutions under the RTS portfolio is important, and also highlights this concept that choosing the right tool for the right job is really important. But with an RTS solution, you've got a huge amount of flexibility to be able to make those decisions, mix and match, and combine those things inside of a given environment. So it's really a portfolio and a technical choice that's able to expand and grow and adapt with the needs that you have both today and as you continue to expand the system.
That's good. And that question does come up a lot. And for everyone on the line and all of your customers, we have a staff here at Bosch that works under Sean's team that can help you design and build up from ground up if you're designing a system or adding on to any existing system at any time. But thanks again for joining us, and we'll see you out in the field.